In this lecture, we focus on sections 2.3 and 2.4. We start with section 2.3. We talk about systems that have infinitely many solutions and those who have no solutions. Since we are talking about systems, then we expect that we deal with planes and lines. Lines when we have two-dimensional problems. If the system includes two variables, x and y, then when we graph them we get lines. So here we have, for example, no solution if this is L1, L2, and if they are coincide, then we have infinitely many solutions. But if we have three variables, then we have what's called a plane rather than a line. So this is plane 1 and this is plane 2 if we have x, y, and z. So when we deal with planes, if two planes may be parallel, so we don't have any solution, as we can see here. P1 is parallel to P2, so there is nothing in common. Or we may have infinitely many solutions in two cases. Either if they intersect, P1 intersects P2, but we know that two planes intersect in a line. The intersection of two planes is a line, not like lines when intersection of two lines is just a point. But here we are dealing with planes, so intersection of two planes give a line. Or infinitely many solutions if they coincide. If they meet everywhere, then they are on the same plane. So in these two later two cases, we call the two planes have infinitely many solutions, or the system that's related to these planes have infinitely many solutions. Now let's start with linear systems with two variables. Last time we discussed this case, how to use Gauss-Jordan elimination method to solve the system. But we'll focus more on or system of three equations. I mean, three equations, three variables. But for now, just as an introduction and to remind you of what we learned from previous lecture, if we have a system like this, let's call this first equation, second equation, we can solve this system by elimination method or substitution method. Those are old methods. Our new method is Gauss-Jordan elimination, and this method is based on matrices. So we write the augmented matrix, so we put the coefficients here and the constant here. So we have the second line 3, 6, 12, and then after writing this we try to make this equal to 1 if it's not already 1, and then we get a unit column. But here this is equal to 1, so we don't have any problem. We need to make this 3 replace it with 0. How to do this? We multiply the first row by -2 and add it to row 2. Put that into, replace that with or put that in row 2. So we have 1, 2, 4. When we multiply by -2, -2 times 1, -2, or I should multiply by -3 because we want to make this equal to 0. 3 equal to, we want to make it 0, so that can happen by adding -3. So when we multiply 1 by -3 and add it to the next row, we get 0 here, and multiply 2 by -3, you get -6, add it to 6, you get 0. Multiply 4 by -3, add it to 12, you get 0. As you can see from this slide, we got a row that's completely or entirely 0. So if we have that case, then we have 0 here equals 0 here. So that means we have infinitely many solutions. Infinitely many solutions. Because you may remember when we dealt with lines, we may have, if we solved equation Now if we solve and we get zeros here, that means infinitely many solutions. If we have some number here, that gives an answer. But if we give here zeros to the left and 5 to the right, 0 cannot equal to number. So 0 equals 5, that's impossible, so no solution in this case. So if we have a line that, or a row that's entirely consists of zeros, that means we have infinitely many solutions. And as you can see, by just multiplying the first row by -3, you get -3x, -6y, -12, and the second row is 3x plus 6y equals 12. Add them, you get 0 here, 0 here, 0 equals 0. That means infinitely many solutions. If you graph those lines, they will coincide. Now, here we have, they coincide if we divide by 3 here. Let's divide the second equation by 3. We get x plus 2y equals 6. By 3 gives 4. We got the first equation. That means those represent the same equation. So when we graph them, we get L1 is equal to L2. That means they meet infinitely many times. So that means we have infinitely many solutions. Now if we have 3 by 3 system, similarly we can solve it using Gauss elimination method. The coefficients, and then the first element, the pivot element, it's equal to 1, so we make everything else in that column equal to 0. So we multiply the first row by -3 and add it to row 2 and put that in row 2. So the first row is 1, 1, 1, 1, and then multiply by -3, we get -3, add it to second row, you get 0. Multiply by -3 here, add it to second row, you get -4. Multiply this by -3, add it to -1, that's -4. Multiply by -3, add to 4, you get 1. And let's do another step in the same matrix. So we want to make this equal to 0. So we multiply the first row by -1 and add it to row 3, and that will be put in that will be our new row 3. So -1 times 1 is -1, plus 1 from the corresponding elements in the third row, you get 0. -1 times 1 plus 5 is 4. -1 times 1 plus 5 is 4. -1 times 1, -1 minus 1, -2. So we got the first unit column. Now for the second column, we look at this number here and we want to make it equal to 1. We can do this by multiplying by -1/4 row 2, because one of the basic or elementary row operations is that we can multiply any row by any number other than 0. So let's multiply the second row by that number. So we get, by multiplying by -1/4, that means we divide by -4, so we get 1, 1 here, -1/4, and the last one stay the same. So we got 1 here. We need to make this 0 and this 0, so we start with the number below. So to make it 0, we multiply the second row by -4 and add it to row 3 and replace row 3. So we multiply by -4. We multiply row 2 by -4. We have 0 here, so that will not affect the 0 in the third row. Multiply by -4, plus 4 is 0. Same thing here. Multiply by -4, you get -4 times -1/4 is 1, plus -1 is -1. As you can see here, we don't need to continue because we got this statement here. We have 0 on the left hand side is equal to -1 on the right hand side, and that's impossible. That means there is no solution for this system. And this means the system, the planes are parallel. Now let's talk about matrices and operations in general. So what do we mean by a matrix? By a matrix we mean any rectangular array of numbers. So matrix is a rectangular array of numbers. For example, this is a matrix. Now we are interested in finding the size. The size is number of rows, 2. We have 2 rows here, times or by number of columns. We have 2 columns here, this and this, and we write it in this form, 2 by 2. We don't write 4 because this is just as simple to mean this is number of rows, this is number of columns, or m and m. It's up to you what any simple can work here. So this is the size of a matrix, or some people prefer to use m and n. Okay, and the numbers inside this matrix are called integers. 2 matrices. Okay, so now let's look at some properties here. We have okay, so this is called row, and this is called column matrix because it consists of 1 column, and the size is 2 rows by 1 column. And this matrix is called row matrix because it consists of 1 row, so we have 1 row by 2 columns. Now we have some properties and some operations here. First thing, we know that the matrix can be denoted as a capital letter. So 2 matrices A and B are equal if 2 conditions are satisfied. First, they have same size, and the second, the corresponding integers are the same. So same size, same corresponding integers. For example, if we know that 1, 2, x, y minus 1, 3, 2 is equal to the matrix 1, 4, z, 2, 1, 2. If we know that they are equal, we want to find x, y, and z. So to find x, y, and z, since we have same size, 2 by 3, 2 rows by 3 columns, and they are equal, we know that they are equal, it's given. That means the corresponding integers are equal. This is equal to this. This is equal to this. X is equal to 4. So x is equal to 4. Y minus 1 is equal to 1. Y minus 1 is equal to 1. Then we solve this, we get y equals 2. So we got the value of y. And here 3 is equal to z. So that's the value of z. Now we have addition, how to add 2 matrices. Addition and subtraction. So to add or subtract, we have, first we ask when can we do that. When? If they have same size. And how? By adding or subtracting corresponding integers. So let's take an example. If we have 1, 3, 4, negative 1, 2, 0, and we want to add the matrix 1, 4, 3, 6, 1, negative 2. So they have same size, 2 rows by 3 columns. So the first condition, the condition is satisfied. And then how? We add or subtract the corresponding elements. Here we have addition, so we add 1 to 1, that's 2, 3 to 4, that's 7, 4 to 3, 7, negative 1 plus 6 is 5, 2 plus 1, 3, 0 plus negative 2, negative 2. And notice that the final answer or the resulting matrix has the same order, 2 by 3. Now one of the properties is that if we want to write this in an abstract way, if we have 2 matrices and we add them, A plus B, and that's possible because they have same size, then this is the same as B plus A. So that means it's commutative. If you add A to B, the same as adding B to A. The second thing, if you add A to B plus C, you can first add B plus C and then add add A, sorry, or you can add A and B and then add C. So this is associativity law, and the first one is commutativity law. Okay, now sometimes we see a matrix that's internally consists of zeros, so that's called zero matrix, and it can be written this way. For example, if it's 1 by 1 size, it's written like this. If it's 2 by 2, it will look like this, and so on. Now we have some property, important property is called transpose. We can consider it as some operation. So transpose. A transpose of a matrix A is denoted as A transpose, and that means we interchange rows and columns. For example, if A is 1, 2, 3, 4, then A transpose, we interchange rows and columns. 1, 2, 3, 4. The row becomes column, and the column becomes row. Now scalar multiplication. For scalar multiplication, we multiply some matrix by a number. Scalar means number, so let's call it C. So we multiply matrix A by C. That means multiply each element or entry of a matrix A by that number C. For example, if C equals 3 and A is 1, 2, 3, 4, then C times A is 3 times the matrix 1, 2, 3, 4, and then we multiply each entry by this 3. So this is 3, this is 6, this is 9, and this is 12. That's called scalar multiplication. Now if we want to find a matrix, let's take an example here, general example. If A is equal to 3, 4, negative 1, 2, and B equals 3, 2, negative 1, and 2, we want to find a matrix X such that 2x plus B equals 3a. We want to find the matrix X. We know the matrices A and B, and we want to find the matrix X. Now how to find the matrix X? Okay, so first we want to isolate X, or we can just do it without isolating it. So there are different ways to solve this problem. Let's just substitute values. So 2 times, what is the size of A and B? It's 2 by 2. So that means X will be 2 by 2 because we added it to B. So that can be happen if they have same size. Addition requires same size. So let's call elements A, B, C, D here in X. This is X. Plus B, what is B? B is 3, 2, negative 1, and 2 equals 3 times A. A is 3, 4, negative 1, 2. And then we solve. So we have scalar times the matrix is, we multiply each entry by that scalar. And then we add to 3, 2, negative 1, 2. And we multiply this scalar by the matrix, we get 9, 12, negative 3, 6. And then we add those two matrices, we add the corresponding elements. Sorry. And this is equal to 9, 12, negative 3, and 6. Now we have two matrices that are equal. So they are equal if the corresponding elements are equal. So we have 2a plus 3 equals 9, but we can solve here. Negative 3, and that gives 2a equals 6, and then divide by 2, you get a equals 3. So we found the value of a. Now we want to find b, so this is equal this, so 2b plus 2 equals 12, then we subtract 2, we get 2b equals 10, that means b equals 5. Now we solve this. 2c minus 1 is equal to negative 3, we add 1, we get 2c equals negative 2, that means c is negative 1. And the last thing, 2d plus 2 equals 6, the corresponding element, and then we subtract 2 to isolate d, we get 4, that means d equals 2. So the matrix X is A, B, C, and D. 3, 5, negative 1, 2. Now next time we'll continue in multiplication, so I'm gonna make another video on multiplication.